Hello guys, so this is the correct chapter 8. We're going to start with 8.1, which is some basic rules of integration. And so a lot of these formulas have been introduced in Calc 1, but here we're just doing an overall introduction again, or review, if you will. Right, so here is the page that contains basically all of the integration formulas, the basic integration formula that we're going to be using. So together, we will be working with some of the examples in this video. Okay, so let's start with example 1 from the textbook. So we see we want to evaluate this definite integral right here. I forgot the dx, right? So if you look at this, there's like basically there's no special formula for that, right? We do see a radical in the denominator and there's a polynomial in the numerator. But one thing you can look for is to see if you have anything in relation between the numerator and denominator, right? So if you look at the polynomial within the radical, the quadratic, right? The derivative of that is going to be the numerator, right? So somehow this is the chain rule of the quadratic is going to be the numerator, right? In cases like this, you can use u substitution, right? And then we're going to let u be a polynomial that's within the radical, right? X squared minus 3x plus 1. Right? And then we can go ahead and find du is going to be 2x minus 3 dx. All right, so you can see that the 2x minus 3 dx appears in the numerator already. So we can go ahead and substitute that in. Right? So this whole thing, let's substitute that in here. All right. So 2x minus 3 dx, that's just going to be du. Right? This whole thing right here is du. Right? Over the square root of the whole thing is u. Okay. Now, next we need to take care of the bounds, right? So the 3 to 5 was in terms of x, right? We want to find out what 3 and 5 is in terms of u, right? So let's just plug in 3. X equal to 3 should be u equal to 1, right? And then we have the relationship between x and u right here. Right? So go ahead and just plug it in, right? So u is equal to 3 squared minus 3 times 3 plus 1, which gives you, that's 9 minus 9 plus 1, that's just 1. All right, when x is 5, we have u is equal to 5 squared minus 3 times 5 plus 1. All right, that's 25 minus 15 plus 1, that's 11. Okay, so in terms of u, after u sub, the bounds is going to go from 1 to 11. All right, so let's fill that in, 1 to 11. And then you can see that starting from something a little more annoying, the integral, we are now back into just a simple power rule, right, with a radical in the denominator. All right, so let's go ahead and fix that and rewrite it in exponent form. So we have u to the power of negative 1/2 du. All right, so integrate that. So power rule, add 1, and then divide by whatever we have left. Right, so add 1, we get 1/2, and then divide by 1/2. Right, and we're evaluating this from 1 to 11. Okay, so that means we have the square root of 11. 2 times the square root of 11, right? If you divide by 1/2, this 2 will be on top, right? 2 radical 11 minus 2 radical 1, which is just 2 radical 11 minus 2, right? And if you want to clear it a little bit, right, you can do factor out the 2, radical 11 minus 1, and then that's approximately 4.63. Okay, so u sub is still very useful. One of the first technique that we learn. And next, let's look at something a little more complicated. All right, example 2, it says complete the square to evaluate this integral right here. Now, most of the time it will tell you to complete the square to evaluate, but let's say if this is not given to us, how would we know to complete the square? All right, so if we look at this integral, right, it doesn't look like we can use u sub because there's nothing in the numerator, and it doesn't look like any of the inverse trig, right? So the only thing we can do with the inside is to complete the square, right? So let's just do that on the side, right? So let's say I have ax minus x squared, right? And let's factor out the negative sign because I like to put x squared before, like that. Okay. And then in order to complete this perfect square trinomial, right, we need to add half of 8 squared, half of negative 8 squared, which is 16, plus 16. And when we add 16, we have to subtract 16 as well. Right, so this part gives me the perfect square, x minus 4 quantity square. All right, so we have something like this, x minus 4 quantity square minus 16. All right, and let's go ahead and put the negative sign back in. So we have 16 minus x minus 4 quantity square. Okay, let's go ahead and put that back into here in the denominator. Okay, so this integral will look like dx 16 minus x minus 4 quantity square and everything inside the square root. Okay, so that actually looks like one of the inverse trig integral, right? So let me clear it a little bit. All right, and we have square root of 4 square minus x minus 4 square. Okay, and let me show you on the screen which one we're looking at. Okay, so the one that we want to be looking at is square subtracting, which is number 18, right here. We have dx over square root of a squared minus x squared, right? So something squared minus x squared, but we don't have x squared exactly, but that's not gonna be a problem. So let's see how this works. Okay, so the formula we're going to be using is going to be on the top right, and we can see that clearly that 4 is going to be our a in this case, right? But instead of x, we have x plus 4. So we want to see if that will cause us any trouble, right? And in order to do that, let's do a u substitution and let u be equal to x minus 4. That means du is just dx, right? So we can just replace dx with du without any problem. And since we're working with an indefinite integral, we don't have to worry about the bounds and stuff. Okay, so let's proceed by working in terms of u. All right, so dx is du now. Square root of 4 square minus u square. Okay, now this integral looks like this, right? And we can just go ahead and apply the formula. That's going to be equal to the inverse of sine of u x over a, so u over 4 plus c. Okay. All right, and now we're not done yet. We have to go ahead and substitute back, right, to perform reverse substitution of u back into x minus 4, right? So that looks like x minus 4 over 4 plus c. Okay, and that's it. All right, let's look at example 3. We're looking at some trig integral. This is actually not one of the examples in the textbook. This is number 14 from the question set. So if you look at this integral, cosecant and sine, they actually don't have any relationship between them. Well, I mean, we can write this as 1 over sine, but that's not going to do anything, right? So here is a technique. Another technique that we can use is by doing by splitting up sine 3t and rewrite it as sine of 2t plus t, right? And then apply the sine trig sum formula, right? So sine of 2t plus t can be written as cosine 2t sine t plus sine 2t cosine t. Okay, and furthermore, we can split out sine 2t as, so cosine 2t sine t plus 2 sine t cosine t times cosine t. All right, so clearing this up a little bit, we have cosine 2t sine t plus 2 sine t cosine t squared. All right, and let's put that back in here. And first, I'm actually going to write cosecant and put it in the denominator as sine. Right, so we have sine 3t over sine t dt. Okay, and we're going to replace sine 3t with this whole thing. Right, so we have cosine 2t sine t plus 2 sine t cosine squared t over sine t dt. Okay, and then we can split them up, and then we can cross out some stuff, right? So this will become sine over sine, so that's just cosine 2t, which is pretty easy to integrate, plus cross that out, that gives me 2 cosine squared t dt. Okay, so we know how to integrate the first term, but not the second term, right? Cosine square. So here is another technique. Usually when you have cosine square, rewrite it as the double angle of cosine. All right, so there are many forms of double angle of cosine, and the one we're going to use should be the one that consists of cosine square, which is this one. Cosine 2x is equal to 2 cosine x squared minus 1. All right, and then we can move the minus 1 over, so we have 2 cosine x squared is equal to cosine 2x plus 1, right? And then that means we can replace this whole thing as cosine 2x plus 1. All right, let's go ahead and do that. So that gives us cosine 2t plus cosine 2t plus 1 dt. Right, and that's just 2 cosine 2t plus 1 dt, right? And it's easy to integrate that, right? The integral of cosine is sine, right? So we have 2 sine 2t, but then we have to divide by the chain rule, which is dividing a 2, and then 1 will just be t plus c, right? And then the 2's is going to simplify out, leaving us just sine 2t plus t plus c. Okay, so there are a lot of trig identity that's being used here, right? For example, the sine of a plus b, and then the double angle of cosine, right? So they are sometimes very useful when you get stuck with an integration that involves trig function, right? So it just takes some time to practice and take some time to identify which one you're going to use. All right, example 4 here is another popular one, right? So let's look at this. We have a rational expression, right, with a polynomial on both top and bottom. You can see that there's actually no relationship between the numerator and denominator, right? But one thing you might notice is that the degree of the numerator is higher than the degree of the denominator, right? So in cases like this, right, we can evaluate this by long division, right? Because after you perform long division, it will become a nicer polynomial for us to work with, right? So now is a good time to refresh on your long division technique. Right? I'm sure many people have different ways of doing it, so just any way that works for you. Right, so my way is the coefficient method. Right, so I'm just going to include the coefficient here. Right, 2 plus 3. Right, 2, so that's 4 plus 6. Subtract, that's -6 minus 7. And then that's minus 3, so it's -6 minus 9. And then we're subtracting, so that will be 2. All right, so that means after long division, my quotient of this rational expression is going to be 2x minus 3 plus 2 over 2x plus 3 dx. Okay. Now, after long division, you'll see that this is actually a very nice polynomial. Well, polynomial here, and then a quotient here, but they are fairly easy to integrate, right? So first one, that's just going to be x squared minus 3x. And this one is actually one of the natural log ones. So I push down 2x plus 3, and then the 2 here is your a chain rule, right? So actually, let's just work it out on the side. Oh, plus 3, right? So I'm going to let u be 2x plus 3. That means du is going to be 2 dx, right? And then that will become du over u, right? Which is just ln of u, right? And that is just ln of 2x plus 3. Okay, so plus ln of 2x plus 3. And then we are evaluating all of them from -1 to 3. Right, so let's just go and do that. 3 squared minus 3 times 3 plus ln of 6 plus 3, that's 9, minus -1 squared is 1, plus 3 plus ln of 1, right, which is 0. All right, so clean this up a little bit. We get 9 minus 9, that's gone. All right, so ln 9 minus 1 plus 3, that's 4. And that's it. ln of 9 minus 3. Oh, not 3, 4. ln of 9 minus 4. Which we can leave it as that. You don't have to punch that into the calculator. All right. All right, example 5. Here is another one that is very interesting. Right? So you can think about it. Which technique would you use? Right? Feel free to pause the video if you want to think about how would you go approaching this integral. All right. So the idea first, we're going to split that into 2 separate radicals. It's actually pretty hard to know what this is going to do, but what we're going to do is we're going to multiply this by 1 plus y on both top and bottom. All right, and we'll see how this goes. All right. By doing so, the numerator is going to be free of the radicals, right? And in the denominator, we have 1 minus y squared dy, right? 1 minus y times 1 plus y, that's 1 minus y squared. All right, and we're going to split that into 2 fractions. 1 over 1 minus y squared plus y over 1 minus y squared dy. And you can we know what this looks like, right? The first one, that's just inverse sine, right? That's just sine inverse. Let's make a note here. All right, this is just the inverse of sine. Y. Okay, and then we need to worry about this next one, right? So let's work it out on this side, right? The integral of y over radical 1 minus y squared dy, right? And now this looks nice. We can just do perform u substitution. Okay, so u is 1 minus y squared. Du is minus 2y dy. Right, that means divide the -2, we get that negative du over 2 is y dy. Right, and then we can replace the whole thing with du. All right, so let's see. That gives us negative du over 2 times the square root of u. Right, and that looks good. All right, let's just clean this up a little bit. It's negative u to the -1/2 over 2 du. All right, so next, just integrate by power rule. We get negative u of 1/2 over 2, and then divide by 1/2, which is multiplied by 2. Right, and we get negative u to the power of 1/2, which is just negative 1 minus y squared within the square root. Okay, now let's just put this back into the original. Okay, so we can integrate both of them. The first part is sine, inverse sine, and then minus square root of 1 minus y squared. And then we are evaluating this from -1 to 0. All right, so sine 0 is 0, minus 1 minus 0, that's 1, minus sine of -1 is inverse sine of -1. So sine is -1 at 3 pi over 2, or actually it's negative pi over 2. Right? I want to stay within the range. So the range of inverse sine goes from negative pi over 2 to positive pi over 2. And minus, that's 1, 1, that's still 0. Okay, so we have pi over 2 minus 1. Okay, and that's it. All right, so a little tricky in the beginning, right? But after that, when you split it up, split into 2 separate fractions, and they'll be easier to integrate. All right, our last example here, we have a definite integral from negative pi over 2 to pi over 2 of x cubed times cosine x dx. Now, for this one, you actually need to do integration by parts. But why do you think this appears here? So notice that the bounds negative pi over 2 to pi over 2, they are the same distance from 0, right? So negative pi over 2 to 0, and then 0 to pi over 2. Now notice that these two functions, x cubed, that's an odd function, right? And cosine x, that's an even function. Okay, so an odd function multiplied by an even function, that's an odd function, right? So if you have odd function that's going away from 0 in the same distance, what you have is something like this, right? So assuming that we're just looking at x cubed, right? And then going from here to here, and negative pi over 2 to pi over 2. So the area underneath the curve, they are exactly opposite of each other, right? The area under the curve here is going to be positive, but the area under the curve here is going to be negative, right? So when you add them, when you integrate x cubed from negative pi over 2 to pi over 2, or actually any odd function for that matter, when you evaluate negative pi over 2 to pi over 2, or any opposite, let's say negative a to a, right? Your integral is always going to be 0 because the area under the curve, they are exactly opposite of each other. And when you add them together, you always get 0. Okay, so that's one thing to look for when you see bounds being opposite of each other. Maybe you can tell, okay, if it's an odd function, then it's 0. If it's an even function, then it's a little different, right? Let's say cosine x, right, dx. Right, if it's an even function, then the area is actually the same. So it's double the area from 0 to a. Okay, and let me give you another illustration. Right? So let's say sine looks like this, right? and then you are evaluating this from, it doesn't have to be negative power 2. Let's just say from this point, negative a to a, right? So that this area is the same as the right-hand side of this area, right? They are the same, right? So you can just find the red area and multiply that by 2, and that will give you the whole integral, the whole area under the curve from negative a to a, right? That's just some tricks and tips that you can use. All right, so that'll be all for 8.1. Of course, there are much more different types of integral, but I'm just showing you some of the interesting ones. Now, of course, feel free to come to my office hour, and then we can work on any of the homework questions together. Thank you, guys.